We shall discuss about shear force diagram and bending moment diagram of simply supported beam today. So we can see that there are 2-point loads, 5 Newton acting at a distance of 0.5 meter from the left hand A and 0.5 meter from the right hand B. Point A and point B are simply supported, and the point loads are applied at the point C and D. The total span of the beam is 3 meters. So let's try to draw the shear force diagram and bending moment diagram. Now proceeding further, this is the simply supported beam that was depicted in the first slide. Here we go. So here you can see that we have the reactions RA and RB. Now let's define what is meant by shear force. Shear force is the summation of all vertical forces at any particular cross section, and the bending moment is algebraic sum of all moments acting at a particular section. So these are the basic definitions of shear force and bending moment. Now, for example, if you make a cut at this section, so to the left of this section, you can see that RA is the only reaction that is acting to the left of the particular cross section. So the shear force at this location will be RA. If you make a cut here, RA. So here also RA. Here also RA. Just to the point, to the left of the point, it will be RA. But if you come exactly at this point, if you reach this point, it will be RA minus 5. Then if you make a cut here, it is RA minus 5. Here also to the left of the section, it is RA minus 5, RA minus 5, RA minus 5, RA minus 5, and it goes on like this until you reach the point D. Once you reach the point D, you can find out here that it is RA, the shear force is RA minus 5 minus 5. So that's the point here. And as you go on continuously reaching here, at this point it will be RA minus 5 minus 5. So here. So similarly, you can also identify the bending moment like that. So with this example, we will try to learn the basics of shear force diagram and bending moment diagram, so that for complicated problems, we will try to understand the meaning of the diagram. Now, here we go. The first thing is to calculate the reactions RA and RB. Now you can see that the loading is symmetric, and directly we can obtain RA and RB as 5 Newton and 5 Newton. But exactly how it happens can be explained by the mathematical equations. So first of all, we will use this equilibrium equation. Summation of all vertical forces is equal to 0. So vertical forces, in the sense, you can see that 5 Newton and 5 Newton is the externally applied load, and these reactions RA and RB are developed as a result of external forces. So these are internal reactions. So if you sum the internal reactions and external forces, it is equal to 0. So here you can see that RA and RA are taken as upwards, and they are taken to be positive, and the 5 Newton and 5 Newton are acting downwards, they are taken to be negative. So it's equal to 0. So on simplification, you get RA plus RB is equal to 10 Newtons. Now this is the equation number 1, and we know that the other equilibrium equation is summation of moment at this point A or summation of moment at this point B is 0. So let's here take summation of moment at A equal to 0, and you can also work in another methodology taking summation of moment at B is equal to 0. Nothing wrong with that, but proceeding further, we can see that the lever arm distance between the reaction RB and point A is nothing but 3 meters, and the lever arm distance between 5 Newton and this point A is 2.5 meters. This is 2.5. And the lever arm distance between point A and 5 Newton is 0.5 meters. So proceeding further, here you can see that summation of moment at A equal to 0, RB multiplied by 3 meters minus 5 into 2.5 meters minus 5 into 0.5 5 inches is equal to 0. So from this you get RB equal to 5 Newton. Now this equation 2, and substitute the value of RB equal to 5 Newton in the equation 1. So you substitute it here, and as a result you get RA equal to 5 Newton and RB equal to 5 Newton. So once you know that the loading is symmetric, directly you can obtain RA and RB. Nothing wrong with that, but this is the mathematical proof of obtaining RA and RB. The next step is to draw the shear force diagram, and the final step would be to draw the bending moment diagram. Now, how to draw the shear force diagram? Now at this location, point A, you can see that the shear force is 5 Newton, because the shear force is the reaction. So wherever you are making a cut at this location, you can see that the shear force to the left of the section is 5 Newton. Once this 5 Newton, which is acting upward, so RA is 5 Newton. So once this 5 Newton reaches this point particularly, you can see that at this point RA is 5 and the downward force is 5, and it reduces to 0. This 0 continues until reaching the point D here. So so the span CD, you can see that it is RA minus 5 minus 5. So here it is 0. Once you reach here, you can find out another 5 Newton acting downwards is present here. So here you can see that shear force at point A is 5 Newton, and at point C is 0, and at point D it is nothing but 5 minus 5 minus 5. Here you can see that the shear force is RA minus 5 minus 5. So RA is 5, as you know here. So here you can see that RA minus external force. So you get minus 5 here. So at this location you have minus 5, and this minus 5 continues until reaching this point B. So this is how we are drawing the shear force diagram. The point is, here you can find arrows. So these arrows are used for convenience, how the shear force is varying between these points. So you can see that the arrow starts from this point and ends at this point. So this is how we draw the shear force diagram. For example, now for the span D, wherever you make some cut to the left portion, you can see that 5 minus 5, it is 0. So this line represents the 0 shear, and at this location you have minus 5 Newton negative shear. So this is positive shear, this is negative shear. So this is how you draw the shear force diagram. Now bending moment. Now while drawing bending moment, there are different methods to find out the bending moment. The first one is simply calculating the bending moment at point A, C, D and B. But the second method, which is very complicated and quite useful for all kind of problems, is using equations. So you can see that bending moment at a distance x from the point A. So you can see that this is the span AC. For span AC we will frame an equation. So from point A to point C, that is the limits are between 0 to 0.5 meter. X can have values only between 0 and 0.5. So this equation is valid only for these limitations. Now bending moment at X is equal to RA times multiplied by X. So wherever you are making cut, it is RA into X. So RA is 5, so it is 5X. Now put X equal to 0. 5 into 0 is 5 here, and put x equal to 0.5, 5 into 0.5, it is 2.5. So if you draw the bending moment diagram, I will tell you that this portion at this point it is 0, and at this location it is 0, it is 2.5. Now I will tell you that also, if you do further calculations, this is the shape of the bending moment diagram. But what we will do, we have found only for the span AC. Now proceeding further, I will explain you for the span CD and for the span dB. So for this, the equation for the span AC is RA times x, and the limits of x is between 0 to 0.5 meter. So at this point it is 0, and at this point C it is 2.5 Newton meter. Now we will frame an equation for the point CD. Now that is a very good question that was asked by the student. Sir, why do you connect these 2 points by line? Why not by curve like this or a curve like this? So this was the question raised by the students. The point is, you look at the equation. The bending moment equation at x is nothing but bending moment equation at x is equal to 5x. So this equation is of the form y equal to mx plus c, where c is equal to 0. Since you get a line equation for the bending moment expression, you can see that you are connecting all the points with lines, and you are not using any curve to connect these points. Now we will write down the equation for the span CD, where you start from this point and end at this point. The x value is between the 0.5, and at this location the x value is 2.5 meter, and at this location the x value is 0.5 meters. So we will frame an equation. So you make a cut here. This is the cut, and this cut is at a distance x from the left hand A. Now the equation is RA into x minus 5 into the lever arm distance is x minus 0.5. So this is also an equation in the, which is a line equation. So this is how you calculate the bending moment at x. So you can see that RAX minus 5 into x minus 0.5. First you substitute the value of x equal to 0.5. So you end up with the value 2.5 Newton meter. Then you substitute the value 2.5. So bending moment at x equal to 2.5. If you substitute that, again you are getting the value of 2.5 Newton meter. So it's very simple that if you frame the equations for these spans AC, CD, and you know the limits of x between these spans, you can easily calculate the values of bending moment. So you can see that at this point the value is 2.5 Newton, and at this point it is 2.5 Newton. So these are constant. You can verify that here it is also 2.5. As I told you earlier, it's 2.5. Okay. Now we have to frame the equations for the portion dB. You can read these equations. As I explained you will find out that the values of bending moment at point C is 2.5 Newton meter. At point D is 2.5 Newton meter. Then proceeding further, now here you can see that the span dB, where the x ranges from 2.5 to 3.5 meters. So here you draw a line which is the cut. This is said to be cut. Okay. Now, so from this point to this point, from point A to this cut, it is x. So the equation will be RA times x minus 5 into this lever arm distance. You look at this figure, RA times x. So you can write down RA into x minus 5 into this is the lever arm distance for this 5 Newton. So it is x minus 0.5. Then for this 5 Newton, it is again minus 5 into the lever arm distance is x minus 2.5. This is the bending moment equation at this for this x. Now the limits are between 2.5 to 3, as you observe from this diagram. It is 2.5 to 3. So it is mentioned here 2.5 to 3. Now this equation I have framed is written here. Then you substitute the value of x equal to 2.5. You get at this point D the value of bending moment is 2.5. Then you substitute the x equal to 3. Once you do that, you finally end up with the bending moment at the point B is 0. So the diagram is 0 bending moment here. Then it is 2.5, 2.5, 0. So in this zone 2.5 is constant. At this point suppose A is present, bending moment is 0, and point B it's also a roller support, bending moment is 0. So you can see the shape of the bending moment diagram, the arrows. Now, clearly I have explained you how to use equations between the span AC and span CD and span DB. You have a cut here and take it as X for the span AC and make a cut here and take this as X and write down the equation for the span CD. So we had 3 equations. So another one is for cut at this location, and here you take X. Then you frame the equations, and once you know the equations for the first equation, the X limit is between 0 to 0.5. For the second equation, it is between X equal to 0.5 to 2.5. And for the third equation, the limits of X is between 2.5 to 3 meters. Yeah. Hope definitely you have understood how to frame the equations for these type of simply supported beams, and how to find out the shear force and how to find out the bending. If you have any doubts, please mention in the comment section and mention your queries. Thanks for watching.